Hello, my name is David Schraub, and I will be presenting with François Hu, Bias Testing and US Regulatory Framework. This is part of the Actual Technologies Summit 2025, and this video will be shown December 11, between 1 and 2 p.m. Central Time. We will go to, after a few words of introduction, we'll get a sense of the issue, going over some definition and the US regulation. Then a case study to really bring this home. François will present a few additional items that he will share the agenda for. A few words for myself. I'm an independent consultant performing appointed actuary and other actual services, as well as performing bias testing to address algorithm with improper discrimination. On the American Academy side, I am a member of the Data Science and Analytic Committee, the AI Subcommittee, the Life Underwriting and Risk Classification Committee. On the SOS side, I am part of the many project oversight groups for research on fairness and long-term care, AI in investment, fairness in life insurance, that type of things. I am an elected member of the Society of Actuaries Emerging Topic Collaborative. I'm also, didn't mention here, a strong volunteer for the International Association of Actuaries. I love to volunteer. A few Calendly, LinkedIn, and email to contact me.
Okay. Let me briefly introduce myself. My name is François Hu, and I lead the Paris R&D Air Lab at Miniman. I joined Miniman in 2024 to work on generative AI, trustworthy AI, and AI ops. Before that, I spent 2 years at Mila in Montreal as a postdoctoral researcher in AI. Earlier in my career, I worked for several years in the bank insurance sector, and during my PhD, I received the award for the best actuarial thesis in France. I'm also quite active in research with publications and reviewer activity in NeurIPS and Triple AI. Today, I'll be talking about algorithmic fairness with a focus on group fairness, which is particularly relevant in insurance. We look at concrete examples, the main fairness metrics, how to apply them in practice, and how remediation can be integrated into the modeling workflow.
So, getting a sense of the issue. I usually go over a few polling questions, and I will go over those slightly differently because of the recording format of this. Let's go to conundrum number one. Designing a product that addresses a specific need of a community is appropriate. And for me, so in the question, which of the following is not an example of bias? The first one, it's not. A special entrance for a fondue set or hot pot related to burn injury is not unduly targeting French cheese fondue lover like me or Chinese from the Chongqing or Sichuan provinces. But it is true, this product should be priced based on the inherent risk of the product and not the ethnicity of the buyer. Odd number, analyzing data for addresses which end with an even number. You probably realize the odd numbers streets are typically on the south and east side of the streets. So that could impact the sun and wind exposure. So having a different price based on that is fair game. That is understandable. Gender-based rating is completely illegal in some countries, but perfectly justified in others. Okay, this one, sexual orientation, I will defer to others to try to justify this one. So this one, conundrum number two, is that a fair representation of a CEO? Now, the word fair is loaded here because statistically it is true. Most CEO of a S&P 500 are white male, between the age of 50 and 70. So, is it statistically a fair representation? Yes, because the computer takes all the images and creates an image similar to it's understandable. However, what do we mean by fair? Is that an appropriate aspirational goal for most members of the US society? That's a different question. Conundrum number two, this one is even more loaded. Most prisoners in the US are white, but it's true. We do have an overrepresentation of Black people in prison compared to their share of the US population. And even more true, we have an overrepresentation in the discourse found on the internet. And that is the underlying training ground of those models. So if you're asking a model, is that a fair representation of a prisoner, the model will come up with that. So let's go over a few definitions. So the Oxford Dictionary defined bias a certain way. You can see here a strong feeling in favor or against a group of people. You can see also the link with unfair, so fairness or inclination or prejudice. So you really see it's a loaded term already. Mathematically, bias, your model is biased if it's not correct, if it's off center. Your model is not biased if it hit the bullseyes. Easy. Fairness. Against, so it was a link with the definition of bias, but fairness has a moral aspect to it. You should pay your fair share. All that type of things really feel it's it's a moral. It's a, so. But mathematically, the premium is a risk. That's what for actuaries what is fair. It's it's a fair if those two are equal. Discrimination. Mathematically, discrimination is separation between the green ball and the white ball, or between between two subpopulation. But in legal term, it's an inappropriate action against a protected class. Really interesting. So, US regulation. You probably have heard of the book, The Weapon of Mass Destruction, on Cathy O'Neill. It was quite impactful. At the same time, the USQS, a US qualification standard, placed a 1 hour bias a CE requirement for all actuaries on an annual basis. So really, you see in the society, there were a lot of, we need to do something. Then it's not, that could go in a wrong place. That could lead to an unfair, unjust society. We want to do something. The NAC model bulletin, which is a bulletin on NAC, on AI model, so it's not a law. Um, they addressed that and they did what I would call mom and apple pie regulation. Thou shall be a good person. Um, so it's not a law. It's derive its authority from a Fair Trade Practice Act, Fair Claim Settlement Practice Act, and all those good laws already on the book. And it's interesting because it's referred to the NIST framework, which is a fantastic framework I would suggest people to look at. Um, how to do risk management for AI models. Really, really interesting. Um, by the way, there are regulations on AI from multiple agencies in the US and around the world. Colorado. Oh, Colorado is here, and Colorado wanted to go beyond the NAIC AI model bulletin and pass this SB 21169 regulation protecting, protecting customer from unfair discrimination in insurance practice. They focused on life, PNC Next, health following, and the key part is that it is already on the book. You have to do it. However, the testing requirements, which really is where the rubber meets the road, are not finalized. Are not finalized because it's difficult. Colorado Department of Insurance proposed some rules. The ACLI proposed also it's a different view. There were other stakeholders that chimed in and so on. The uh, the department mentioned that they will have an updated version in 2020 Q1. So it's still waiting for it. So it's difficult. Georgia Auto, the so same is the testing requirement in its infancy. They did a data call in order to understand how in order to be able to really think. That slide is even behind the data call yet. Hold on, please. So New York, one is final. This one is final. Um, and this one is not a law. It's just the New York interpretation of those all good act regulation. Um, so the scope is slightly different, understood. Um, I want to bring the attention on section 15 and 18. You need to assess variable after variable and see if there is a legitimate reason to use it. Yes, um, if there isn't an alternative variable that has the same predictive power but is less discriminatory against a protected class. And looking at all potential alternative variables, that is a costly endeavor. Section 18 is interesting because Section 18 is suggesting a few metrics to look at, but let the insurance company pick the right metrics based on the issue at hand. So that is quite interesting. Okay, other states. Connecticut has an annual certification, quite interesting. Texas, this one is also key because they define intent. They define if the insurance company didn't intend to discriminate, um, it's it's probably okay. So really, what it means is that the burden of proof to sue the insurance company is much higher compared to Colorado, where regardless of your intent, if the result of your process and procedure lead to some price differences, then you are in trouble. In Illinois, uh, regulation has been passed really close to the NAIC model bulletin. Next is a case study. I had the privilege to test a tool to test see if the tool was biased or not. So what is the tool? Digital Owl is the name of the company. They provide live underwriting support. So it works. You feed the machine a huge PDF. You feed it of and it looks at page 72, page 226, and so on. Each doctor visit, each BMI, and it charges the BMI over time. So it summarizes the large medical provide insight and it's throw a decision tree on it and gets you to a weight gain, red flag, heart failure, yellow flag. Why the tool did that? Because it picked this item from the medical file and the medical file. So, uh, what's legal? So technically, Digital Owl is a separate company, so it would follow the third-party data and model. So the H committee from the NAIC, or you can follow the New York circular letter. And the New York circular letter really said, please manage your third-party vendor, which is similar to what the NAIC H committee says. So let's go to the most stringent one, the ACLI proposed draft regulation on the Colorado B21-160. So let's go section. Okay, section 5, you should BASFG's Bayesian's improved name geocoding, which means let's take a caricatural example, a fake one. Roberto Ramirez living in Little Mexico has 83% chance to be Hispanic and 3% chance to be white and whatever. So assigning a probability based on first name, last name, and and location. So that's if you don't your file, you do that, and then you can see um, uh, people, all the white people, all the Asian people to see if they are discriminating against. Um, are they are they discriminating against by having a more red flag than the other? So that's what you want to manage. And how you need to do Section 6B says you need to test without race, test with race, and build a model without, build a model with, see if those two models are vastly different. If they are, it means you have a problem. So it doesn't work for this one. So we did Section 7A, take any statistical method. And what we did is we did a synthetic file. We create a synthetic file and um, from a simple case, and we do the manual testing triggered by that sample, by that file. And we found in one case, the tool miscomputed age. And because of that, following the workflow, taking the account the error above, it land in the wrong place, but not because of protected class, but because of age calculation incorrect. So the conclusion is that the model was not biased because it was not unduly biased against one protected class. Thank you for that. I will be there for Q&A, and now Francois will cover his sections.
After David's part on the legal rules, I want to show another important point. Fairness problems also create big reputational risks. Here are a few examples from different sectors. First, in health scoring, a well known study showed that an algorithm used in hospitals gave lower risk scores to black patients, even when they were actually sicker. This case became quite famous and created a lot of public concern about fairness in healthcare algorithms. Second, in fraud detection. In France, an investigation showed that the system used by the family allowance fund relied a lot on protected attributes like disability and family status. Third, in insurance claim. A recent study found that claims coming from areas with more black residents were less likely to be paid and the payouts were usually lower. This was widely discussed in the media and raised doubts about how fair claim processes really are. We can therefore see that fairness issues can quickly turn into public problems and they can strongly affect trust. This is why fairness is not only a legal topic, it is also a key part of protecting the reputation of any organization. Let me give a short overview of what we mean by fairness and explain the different ways we can look at discrimination. Fairness is linked to unjustified discrimination, meaning that people are treated differently simply because they belong to a certain group, such as gender, age, or ethnicity. There are several ways to study discrimination. The first view is a group fairness. Here we ask a simple question. Are different groups receiving different outcomes? For example, do two groups get different approval rates, different prices, or different claim decisions? This perspective is widely used in practice, especially in audits and regulatory reviews. And the reason to that is simple because it provides actually a clear and measurable signal. This is why in the rest of the presentation, we will mainly focus on group fairness. The second view is individual fairness, which checks whether similar individuals are treated in the same way. The third view is counterfactual fairness. Here we imagine changing only the sensitive attribute, for example, changing the gender, and we check whether the decision would stay the same. Now, the diagram on the right shows that fairness is not only a technical question. It sits at the intersection of three areas. The first area is the application domain. What is considered fair in P&C can be very different from what is considered fair in health or life insurance. The second area is stakeholder expectations. Clients, regulators, actuaries, and data scientists may have different views on what fairness means and how far we should go to achieve it. And third, the societal context. Fairness evolves with social norms, legal rules, and cultural sensitivity. So, what society considers fair today may change tomorrow. When these three areas overlap, that is where our practical definition of fairness emerges. On this slide, I want to introduce two key metrics that help us measure group fairness. There These are actually the two common ways to check whether a model treats group differently. The first metric is demographic parity. Here, the idea is very simple. The model should give the same prediction rate for the two groups. For example, if women and men both receive a positive prediction in 2% of cases, then the model satisfies demographic parity. This metric is useful when the true risk doesn't really depend on the sensitive attribute or when the minority group is underrepresented in the data. But there is an important limitations here. Demographic parity ignores real differences in risk between groups. So if the true risk is different, this metric can be misleading. The second metric is equality of opportunity. This one focuses on model performance. We check whether the model is equally good for both groups, especially when the true positive rate is the same. For example, if the model correctly predicts a severe insurance claim, like 97 percent of the time for both women and men, then it satisfies what we call equality of opportunity. This metric works well when the true risk is genuinely linked to the sensitive attributes and when there is no strong bias in how the data was collected. There is an important reminder here. These two metrics are not compatible with each other. You usually cannot satisfy both at the same time because they come from different views of what fairness should mean. So the key message is both metrics are useful, but they apply to different situations, and it is important to choose the one that fits the context. In order to understand mathematically the different fairness criteria, I want to introduce a simple but important idea. When we analyze group fairness, we always compare two confusion matrices, one for each value of the sensitive attributes. For example, men on the left and women on the right. Each group has its own true negatives, false negatives, and true positives. And each group has also its own error rates, like the true positive rate or the positive predictive value. So even if we use one single model, it can behave differently across groups simply because the underlying data distribution is different. This is why we need to look at these matrices separately. This slide is just to show the structure, one confusion matrix per group, and all the performance indicators that we might compare. In the next slide, we will use this framework to understand different group fairness definitions. Now let's look at the demographic parity. Here we focus only on the predictions made by the model. How often it predicts 0, how often it predicts 1. On the slide, you see these prediction blocks highlighted in blue for the two groups. For demographic parities, the idea is simple. The distribution of predictions should be the same across the two groups. So the probability of predicting 0 should be the same for group minus 1 and group plus 1. If these blue columns are equal, then the model is fair according to this notion. Let me give a small connection to the USO. Interestingly, if we allow some tolerance, meaning that we don't require perfect equality, then it becomes to what the US regulation call disparate impact, which checks that selection rates across groups are not too different. Here we focus on the performance of the model, especially for people who truly belong to the positive class. For example, people who actually have a claim. On the slide, the green blocks show the true positive rate and the false positive rate. Equality of opportunity means that these values should be the same for both groups. A simple insurance example is fraud detection. If two people commit the same fraud, the model should detect them at the same rate. One group should not be flagged more often than the other when they truly belong to the positive class. So, in one word, equality of opportunity is about fair performance. Now, let's look at the third perspective, predictive parity. This perspective tells us how reliable the model's prediction is. For example, how often a predicted 1 is truly a 1, and how often a predicted 0 is truly a 0. Predictive parity simply means that these predictive values should be the same for both groups. So, for example, when the model predicts high risk, that prediction should be equally reliable for group minus 1 and group plus 1. You may remember the hospital example from the introduction slide. Patients with the same risk score didn't have the same true medical needs across groups. In other words, this is exactly a violation of predictive parity. Now, once we understand how to quantify all these biases, the next question is where in the modeling process should we act to reduce bias? And that's exactly what the following slide shows. This slide summarizes the three main families of techniques to reduce bias, depending on where we intervene in the modeling pipeline. The first option is preprocessing. Here we fix the data before training the model, for example, by correcting bias features. The advantage is that it works with any model, but the limitation is that we don't directly control the bias of the financial predictions. The second option is in processing. This means adding fairness constraint directly inside the model training step. It keeps the model structure consistent, which is important in regulated environments, but it depends heavily on the model class and can be more time consuming. The third option is post-processing. Here we adjust the predictions after the model is trained to meet fairness constraints. Direct control on the fairness matrix and works with any model. But this give you also one downside is that the final predictive predictions may no longer follow the structure of the original model. For example, they may no longer behave like a GLM. In practice, the right choice depends on your constraints: data constraints, model constraints, regulatory constraints, or how much transparency you need. As a conclusion, let me briefly highlight two recent developments on our side that connects directly to the final topics we covered. For this last part, I just want to highlight one of our recent contributions developed by Bertie Tierney from our AI lab and Arthur Charpentier from UCAM. As you know, linear models are still widely used in insurance and other regulated areas because they are simple, transparent, and easy to justify. But as soon as we impose a fairness constraint like demographic parity, it becomes very difficult to see how the coefficients are modified and where the remaining bias actually comes from. To address this, we developed a post-processing framework that works on top of any linear model and it doesn't require retraining. The method decomposes the remaining bias into the direct bias, so coming from the sensitive attribute itself, and indirect bias coming from correlated features. This gives a very clear feature level view of how demographic parity reshapes the model and where unfairness may still persist. And because it works without touching the original model, it is very practical for auditing, regulatory reviews, and quick mitigation. To conclude, here is a quick overview of the main fairness packages available today. Most existing Python library focus on demographic parity or equality odds, and mostly for binary classification. AIF from IBM provides, for example, strong preprocessing tools. Fairlearn from Microsoft offers solid in-processing methods for classification, and Google's fairness indicators mainly support monitoring without remediation. Our package, which is called Equipy, implements a flexible and a post-processing approach that handles multiple sensitive attributes at once. It covers actually some capabilities that current open source solutions do not yet provide. Thank you very much for your attention. I'd be very happy to take any questions.